Hi everyone. Today we're going to be talking about transformers in the context of the conservation of energy. Remember that the conservation of energy states that we can't create or destroy energy. So how is it that we can increase or decrease the voltage of a signal without creating or destroying energy? Well, let's find out. So the principle of conservation of energy states that energy cannot be created or destroyed, right? You remember that? This fellow over here was the one who figured out that heat energy and mechanical energy could be changed into one another. He was called Joule, and there's a unit of measurement named after him. Energy can only be transformed from one form to another. And this remains the case for a transformer. So a transformer is not able to break the conservation of energy. It can only transform energy from one form to another. So in a transformer, there are two transformations of energy. Can you see where they are? The electrical energy in the primary coil is transformed into the energy of the magnetic field. So this is the first transformation of energy. Now, during this process, there can be eddy currents created, which will dissipate some of the energy. So there's a little bit of energy loss. The magnetic field energy is transformed back into electrical energy once it reaches the secondary coil. And this is the second transformation of energy. So ideally, we don't lose any energy when we make either of these transformations. In reality, of course, that's not really the case. So a transformer that does not lose energy, and this sort of transformer is used a lot in physics questions, is called an ideal transformer. The amount of energy that's carried through a wire every second is called its power. We've studied it a bit before. It's given by P equals VI, where V is the voltage drop across whatever's carrying the power, and I is the current through it. So the total power given off by an energy source is given by the voltage of the energy source multiplied by the current being drawn from it. This equation can be used to find the power of a transformer's primary coil, right? Energy is going to be conserved, and this means that the energy in the secondary coil will be equal to the energy in the primary coil, and so their power will be equal as well. Power is simply energy over time. So if we have an ideal transformer, which means that no energy is lost, then the input power, V1I1, will equal the output power, V2I2. And so we can rearrange this to figure out any single one of these variables if we know the other ones. So the change in current is inversely proportional to the change in voltage. If we double the current, we halve the voltage. If we double the voltage, we halve the current. So remembering that V1 over V2 equals N1 over N2, which we've already learned, that is, the ratio of the voltages in the primary and secondary coils of a transformer are equal to the ratio of the number of turns. We have I2 over I1 equals N1 over N2, right? So the ratios are flipped over. Now, in reality, there's no such thing as an ideal transformer. Even the best transformers lose a small amount of energy, even if they have laminated cores. So there is no such thing as a transformer that is ideal, although it is very useful to use in mathematics or in theoretical physics, because it makes the maths very easy. The efficiency of a transformer is a measure of how much energy gets from the primary coil of the transformer to the secondary coil of the transformer. An ideal transformer has an efficiency of 100%. A transformer that is only 95% efficient only gets 95% of the energy from the primary coil to the secondary coil. The rest is lost by things like eddy currents. So this is the end of the theory. In this section we've talked about transformers and how they change the current of the signal passing through them as their voltage changes. Let's go on to some questions. Question 6. The secondary coil of an ideal transformer, I told you we'd be seeing them a lot, has twice as many turns as the primary coil. If 3 amps flow through the primary coil, what current flows through the secondary coil? So if the secondary coil of the ideal transformer has twice as many turns as the primary coil, that means that the voltage is going to be greater than the primary coil, right? It's a step-up transformer. But if the voltage is stepped up, that means that the current is stepped down by the same factor. So the current in the secondary coil will need to be less than 3.0 amps. And there's only one option that does that, which is A, 1.5 amps. The voltage of the secondary coil is twice that of the primary coil, which means that assuming energy is conserved and we have an ideal transformer, the current in the secondary coil will be half of that in the primary coil. Question 7. If a transformer is 95% efficient, that means that either it transforms one voltage to another 95% as quickly as it could, it transforms one voltage to another while keeping 95% of the maximum energy, it transforms one voltage to another 95% as large as the first voltage, or its construction uses up 95% of the materials used to build it. Our correct answer is not in fact A, but B. Sometimes efficiency is used to talk about how quickly something can get done. In this context, we talk about maximizing the energy that we get from one coil of the transformer to the other. So if we maximize efficiency, we minimize energy loss. Question 8. 90 watts of AC electricity are sent into an ideal step-up transformer that increases its voltage by 50%. If voltage of the electricity in the primary coil is 30 volts, find the current in the primary coil. Now, in order to find the current in the primary coil, we need to use this equation. I equals P on V. Substituting in 90 watts and 30 volts, we end up with an answer of 90 over 30, or 3 amps for the current. Part B, find the voltage in the secondary coil. Now, because we have a step-up transformer that increases the voltage by 50%, this is quite easy. The primary coil is 30 volts, and multiplying this by 1.5, that is, increasing it by 50%, gives us an answer of 45 volts. Finally, find the current in the secondary coil. So in this case, we can once again use our equation I equals P on V. Now this time, our power will be exactly the same because we have an ideal transformer, but the voltage will be different. It'll be 45 volts. So substituting these numbers, we end up with 90 over 45, which gives us 2 amps, which is a decrease of 1/3, which corresponds to an increase of 50%. That's because 2/3 is the reciprocal of 3/2. Question 9. In a 1 to 3 step-down transformer, a current of 1.5 amps flows through the secondary coil. What was the input current if no power was lost? So we have a step-down transformer, right? That means that the voltage in the primary coil will be higher than the voltage in the secondary coil, right? Now, if the voltage in the primary coil is greater than the voltage in the secondary coil, the current in the primary coil must be less than the current in the secondary coil. So if the secondary coil has a current of 1.5 amps, the primary coil must have a current that is less than this. So if the output is 1.5 amps, the input current must be 1/3 as much. So in a step-down transformer, current increases by the same factor as voltage decreases, and the current is 0.5 amps in the primary coil. Part B. If there are 300 turns in the primary coil, how many turns are in the secondary coil? Now, if it's a step-down transformer, it means there need to be less turns in the secondary coil than in the primary coil, and the ratio is 1:3. So our answer is going to have to be 100 turns in the secondary coil. Question 10. Is the amount of power transferred into a transformer's secondary coil equal to the power transmitted by the primary coil? Explain your answer. So be careful here. In physics, we have a tendency to use ideal transformers a lot. But in reality, of course, these don't exist. So our answer here is going to have to be no. It is not the same, although it may be very, very similar. Upwards of 99% efficiency, in fact. So it follows from the conservation of energy that there cannot be more power in the secondary coil than in the primary coil. And because there's always some energy lost, due to eddy currents and so on, the energy in the secondary coil will need to be less than the energy in the primary coil, although it may be very similar. So that's the end of the questions. In this section, we've learned something about the currents that flow through transformers and how the currents change based on how the voltages change. It's simply the reverse ratio. If the voltage doubles, then the current halves.